I have a piece of plastic in which I've drilled 2 holes. I've taken a piece of dowel rod and sawed it in half, and I'm going to place it on both sides of the plastic and use it as a form so that I can wind a coil. So I'm going to take magnet wire, thread it through the holes and around the dowel rod to construct the coil. I have now wound the coil. It's 25 turns. Now I will remove the dowel rod pieces from the 2 sides. So here's our 25 turn coil with the piece of plastic down the center. Now I'm going to sprinkle on some iron filings. I have sprinkled on some iron filings, and they're going to be randomly oriented. So now I'm going to apply a current to the coil, which will generate a magnetic field. And what will happen is that the iron filings will become magnetized and rotate along the magnetic field lines, so we'll be able to visualize the generated magnetic field lines. So now I'm going to turn on the current, and I might have to tap it a little bit to get the iron filings to rotate. Inside the coil, you can clearly see how the iron filings have rotated along the magnetic field lines. As you move away from the coil, you can see how those field lines start to spread out. Now, if you look at the left edge here, you can see how those magnetic field lines form closed paths around the coil. In fact, any of these magnetic field lines will form closed paths, but you can't see that for some of these because as you get farther away from the coil, the magnetic field was not strong enough to rotate the iron filings. We have visualized the magnetic field lines for current going around in a circle. So here is a sketch to illustrate what those magnetic field lines look like. Now let's look at the magnetic field generated by a coil of this shape. So the first thing I want to talk about is how I constructed this coil with the piece of plastic down the center of the coil. I have a piece of plastic that has a protective layer on each side. And the type of plastic I have is polycarbonate. And I'm using polycarbonate because you can drill it without it cracking. Now, I have a template that I place on the plastic like this, and then drilled the holes through the plastic. And after drilling the holes, it looks something like this. Now I have a dowel rod that I've taken and sawed down the middle so I can place it on both sides of the plastic. So now I had a form where I could go and take a wire and thread it through the holes and around the dowel rod to create my coil. So I've wound the coil, and I actually threaded the wire through each hole twice. So this will double the number of turns per unit length. Later we'll see that for a given current, doubling the number of turns per unit length will double the generated magnetic field intensity. So now I'm going to remove the dowel rods. So we now have our coil with the sheet of plastic down the center of the coil. I'm now going to sprinkle on some iron filings onto the plastic sheet. The iron filings are randomly oriented. When I apply a current to the coil, a magnetic field will be generated. This magnetic field will magnetize the iron filings, and they will rotate and align along this magnetic field. So now I'm going to apply a current, and I'm going to tap to help the filings align along the magnetic field. Inside the coil, the iron filings have all rotated to align along the length of the coil. Let me zoom in on this end. So you can see how they've aligned, and as they exit the coil, they quickly spread out and the field becomes weak and the filings outside the coil do not rotate. These magnetic field lines that are exiting the coil here on the left end will have to spread out and circle around and come back in the right side of the coil. So because of this spreading, the field outside of the coil is going to be extremely weak compared to the field inside the coil. Here's a sketch of what we found for the magnetic field generated by a coil as shown here. We found that there was a large magnetic field inside, but when that field emerged from the coil, it spread out quickly because it has to wrap around and come back in the other end of the coil. So the field quickly gets very weak everywhere outside of the coil. Now that we know the form of the magnetic field intensity, we can apply Ampere's circuit law to determine the value of the magnetic field intensity. So Ampere's circuit law is that the integral of H dot dl around a closed loop is equal to the current enclosed. Our path of integration will be down the inside of the coil, so we'll be tracing a path in the same direction as the magnetic field inside the coil. When we get outside of the coil, we'll turn in 90 degrees and essentially be moving perpendicular to the field. Then we'll turn again 90 degrees and integrate along the coil but outside the coil, and then again when we get to the other end of the coil, turn 90 degrees and essentially be going perpendicular to the field again. So there's our closed path of integration. When we're integrating along the path inside the coil, the integral of H dot dl will just be the value of H inside the coil times the length of the coil. So let's call the length of the coil L. When we're integrating the two ends, these path lengths are short and are pretty much perpendicular to the magnetic field, so H dot dl will essentially be 0 or close to 0, so that we can ignore the contributions from the two ends. Also, the magnetic field intensity is very weak along the path outside the coil, so we're going to ignore it compared to the value of H dot dl inside the coil. So essentially the integral of H dot dl around that path will be the value of H inside the coil times the length of the coil. So now we have to determine the current enclosed by our path. So that will be the current going through this area right here defined by our path of integration. Here's a view of the path of integration with an actual coil, and the path is traced on the piece of plastic that's cutting through the center of the coil. So the lower part of the path is on the inside of the coil. So the coil pierces the surface defined by the path each time it goes around. So if the coil has n turns, it's going to pierce that surface n times. And each time, if there's a current I flowing through the coil, each time it pierces the surface, there's a current I going into the plastic. So if there's a total of n turns, there's a total current going through the surface defined by the path of integration of n times I. Our coil is of length L and it has n turns. Now the current enclosed will be the current going through the surface here that is defined by our path of integration. Now the coil pierces that surface n times, and each time it pierces there's a current flowing into the page. So the current enclosed will be the number of turns times the current flowing in the coil I. And we have to use the right-hand rule when applying Ampere's circle law. So we put the fingers of our right hand in the direction of integration. And when we do that, our thumb points into this surface defined by that path of integration, and the current is flowing in the direction of our right thumb. So in that case, the current enclosed is positive. So inside the coil, the magnetic field intensity is the number of turns times the current that's flowing in the coil divided by the length, and the magnetic field intensity outside is very weak, except, as we mentioned, very near the opening, so we'll just consider it as 0. So the strength of the magnetic field intensity will scale with the number of turns per unit length for the coil. Also, the direction of the magnetic field intensity is along the length of the coil. Our path of integration could have been anywhere inside the coil, and we would have gotten the same result. So that tells us that the magnetic field intensity is the same everywhere inside the coil with a value of Ni over L.